Hello everyone, I am a verified educator at Unacademy and I take online live classes for CSIR, UGC NET and GATE chemistry preparation. To access my classes on Unacademy, you have to take Unacademy Plus subscription and that you can take for the time you want, either for 1 month, 3 months, 6 months or 12 months. While taking subscription, you can use my referral code, that is N underscore Huda, to get 10% discount on the referral fee as well as to get access to my WhatsApp group. So if you guys are interested in learning live from me, you can take an Academy Plus subscription and join my classes over there. Now let's continue with our video. Hello everyone and welcome to the channel. So as promised to you guys, I'm going to start this series on chemical thermodynamics, and this video is going to be about basics, right? So I'll be starting from the basics, and I'll be explaining you because ideally it should start from system and surrounding. So I'll not waste much time on this. I'll just quickly start from there, and I'll also cover up some of the important things like different processes are there, what are the different conditions in them. So moving forward, we'll cover each and every part from this chemical thermodynamics, right? So what is system and surrounding? That's what the question arises. So system and surrounding, this is something which from which your thermodynamics actually starts. Thermodynamics, let me tell you that it's the study of how your heat is flowing in the system, right? Or how the heat exchange is taking place. So system is the part of the universe which you are studying, like for which the thermodynamic study is being done, and surrounding is the rest of the part for which you are not doing anything. Okay. Now, having said that, your system is of three types. Okay. So your system can be of three types. It can be either open system, it can be either closed system, okay, or it can be like isolated system. So, to explain this, to understand this, the basic one example we'll take. Open system is, let's say you are cooking or you are making tea. Okay, you are making tea in an open kettle. So that's a open system. Okay, if you are making tea in an open kettle, that's a open system. Now, that means on that particular system, what is happening? That energy, okay, or heat. Basically, energy means heat, so heat plus matter both is exchanging between system and surrounding, right? So you are studying or you are taking care of that kettle, and the surrounding is the rest of the part, rest of the universe. So your energy or the heat is being taken, like it is getting transferred from your kettle to the surrounding, right? And also with the help of evaporation, some part of your water vapor is also going there. So energy, that means heat plus matter, both is being transferred or both has been exchanged between the system and surrounding. So that's called as open system. Talking about closed system, now what I'm going to do, just going to put a lid over there. Okay, on the same kettle I'm going to put the lid. Now what is going to happen? Only energy or only heat is now going to be transferred between the system and surrounding. No matter can be transferred because I have put a lid over there. Okay, so that's a closed system. In the isolated system, just imagine that same tea you have kept in a thermoflask. Okay, now since the tea is in the thermoflask, so ideal, if it is an ideal thermoflask, that means there is no exchange of heat, neither exchange of matter is taking place. So neither heat nor matter is getting exchanged between your between the like system and the surrounding, right? So that's what is the basic like that's the basic way how you can understand these three things. All right, so now let's talk about different types of, like, since we are done with the system, so let's talk about different processes. Okay, so there are many thermodynamic processes for which we have to see that what are the conditions for them. So let's do that. All right, so let's talk about thermodynamic processes. So there can be, like, depending upon the conditions, there can be many types of processes. Let's start from your isothermal process. Okay, we all know about it, that in the isothermal process, temperature is constant. Okay, T is constant over here. So mathematically, how you express T as constant, we say that dt is equals to 0. That means change in temperature is 0. That's what it is. Now, for such processes, you have certain more condition. First is that it follows Boyle's law. Okay, so it will follow anything under the isothermal condition will follow Boyle's law. Okay, then you have, like, the work done in the isothermal process is graphically area under the PV curve. That's also one thing. Okay, so work done is area under PV curve, right? The next condition is that your delta H is equals to 0 in your isothermal process and your delta U is equals to 0 in the isothermal process. Okay, so these are
some of the conditions for your isothermal process. Now let's talk about adiabatic process. Okay, so isothermal, where there was no change in the temperature, or the temperature change was zero. In the adiabatic process, what happens that there is no exchange of heat between the system and surrounding. So the exchange of heat is not there between system and surrounding. So this type of process, in this type of process, the heat given to the system, or Q, is constant. Okay, this is constant, or mathematically we will say that dq will be equal to 0. So that's what happens in your adiabatic process. Okay, next comes your isobaric process. Now, as the name suggests, iso means same, bar is a unit of pressure, so like that you can remember. So here what will happen, that the pressure is constant. Okay, so the pressure is constant in this case, so your dp will be equal to 0 in this particular case. Then comes your polytropic process. In the polytropic process, what happens, that heat capacity of the system remains constant. That means heat capacity of the body remains constant over here. So we can say that dcp is equals to 0, or you can say that dcv is also equal to 0. So both the heat capacities, either at constant pressure or at constant volume, they will be equal to 0. That's what it is. Next is your isochoric process. So you have isochoric process. Okay, so what will happen in the isochoric process? So over here your change in volume will be 0. Okay, so there will be no change in volume. Your volume will remain constant in this particular case. All right. Now you might have heard about bomb calorimetry, right? So that process, or that combustion of a substance in the bomb calorimetry, is actually an example of isochoric process. All right. Alright, so processes can also be categorized as reversible or irreversible process. Reversible process is a process in which, if a certain change is happening in the system, and if you reverse that particular process, okay, if you reverse that particular process, then the change will be nullified, okay, or the change will happen in the opposite direction. That's what it is. Whereas in the irreversible process, this does not happen. Generally, your spontaneous processes, okay, spontaneous processes are irreversible processes, which only take place in a forward direction, which cannot be reversed. So spontaneous processes are example of your irreversible processes. All right, so now let's talk about work. Okay, so ideally work is actually equal to negative of P external into V2 minus V1. Okay, so P external is the external pressure which you are applying, and V2 and V1 are the volume. V2 is the final volume, V1 is the initial volume of the system. So the difference in the change, or the change in the volume multiplied by the external pressure, actually gives you the work done by the system. Okay, now there can be two things. Either you can have that your V2 is greater than V1. This could happen when there is expansion, right? When there is expansion, in that case your work done will be negative. Okay, in that case your work done will be negative. Whereas you can have that V1 is greater than V2, and this can happen when you have compression. Okay, in the case of compression, and in that case your work done will become positive. So this also you should know, that when your work will be negative and positive, so in the case of expansion it will be negative, in the case of a compression it will be positive. Now, depending upon different processes, we have different equations of work. So let's see that how this particular work changes when the system, or when the process changes. Alright, so we'll talk about isothermal reversible expansion of the ideal gas. In this case, what is the equation of work? So as we know that work is equals to minus P dV. For very small change in volume, we can write it like V2 minus V1 as dV over here. So here P is your P external basically. So yeah, so it is for a very small value of work done, right? So if you want to see for the whole system, so for the complete system, if you want, you just have to integrate this equation. So it will become minus integration of P dV. Now you can use ideal gas equation in order to put the value of P. So we know that PV is equals to nRT. Just substitute the value of P. So that will be nRT by V. Just substitute it over here. So integration of W will become W this side on the right hand side, whereas on the left hand side, whereas on the right hand side we have minus nRT dV by V, because other things are constant. It's an isothermal process, so temperature will also be constant, so that I have taken out. Other things will get integrated, so the integral of 1 by V will be ln V, right? So that is going to give you the final equation. I'm just going to write down like this, so that will be minus nRT ln V. Okay, that's what you are going to get, and basically you will get a constant as well, but since volume you are changing from V1 to V2, so you can write down it like V2 by V1. Okay, so that's how you can write, or you can convert this equation in the terms of log base 10. So it will be minus 2.303 nRT, and it will be log V2 by V1. Remember this, that when you are putting negative sign V2 by V1, it will be, if somewhere in the book you can also find like in the positive sign. So there we will be having V1 by V2. All right. N is the number of moles, R is the gas constant, T is the temperature at which you are doing all these things. So this is the formula for work done in the isothermal reversible expansion of the gas. So that's how it is done. It's pretty simple. It's pretty straightforward formula. Now let's say that yeah. So one more thing, that work done in the isothermal process will always be, because it's an expansion, right? So this value will be greater than this. So obviously this whole value is going to be positive. So overall your work will always be negative. So this is also something, that work done in isothermal process, okay, that is going to be always negative. So work done in isothermal process is negative always. All right, so let's talk about the next process, like the next process in which work done we have to calculate. So let's say that instead of reversible process, we have irreversible process. Okay, so instead of reversible, now we have irreversible process. So what will be the isothermal irreversible expansion of ideal gas? How you are going to get the equation? So work done will be again the same thing, that is minus P external, and it will be V2 minus even. That's the equation which you will use. Now if let's say this whole thing is being done in vacuum, okay, if if you want to find out the work done under the irreversible expansion of ideal gas in vacuum, so what is going to happen? Now in vacuum we know that the P external pressure is going to be 0. So here your work done will also become 0. Okay, so in that vacuum your work done will be equal to 0. Whereas if the vacuum is not given, if the general condition is given, then you will be having work done given by this particular equation in the irreversible expansion. Now let's talk about reversible adiabatic expansion of the ideal gas. Now under this reversible adiabatic expansion of gas, there are 2 or 3 very important equations over here. I'll not go in the derivation of it, you can find it out from the books, but I'm just going to give you the formula. Okay, so if you go with that, the first formula is this, that is T V to the power gamma minus 1 is equals to constant. Okay, where gamma you all know it's Cp by Cv. Okay, that's the ratio of like heat capacity at constant pressure divided by heat capacity at constant volume. Then again you have one more equation, that is given by PV to the power gamma is equals to constant. Now we have a lot of questions which have been asked from this particular thing in our CSIR-NET exam, where we have to use this equation in order to derive the final answer, or in order to get the final answer. Okay, the same question, like the question on this equation was asked in, I think, in CSIR June 2018 exam, as far as I remember. There were more questions from here, but yeah, from there it was asked. So the question was not directly from this, but yeah, you have to use this particular equation in order to derive, or in order to get the value of pressure, and then you have to put it to get the answer back. So this is very important equation, right? So you should remember these two. So again, to calculate the work done in this process, just by using the same equation, that is dW is equals to minus PdV, and putting the value of pressure from this equation to here, and then integrating and all. At the end, what equation of work done you are going to get for reversible adiabatic expansion of gas? You are going to get work done is equals to 1 upon gamma minus 1, and in the bracket you have P2 V2 minus P1 V1. Okay, so that's one of the equation for work done in your reversible adiabatic expansion of the gas. One more, in the terms of your temperature is given by this, since it's not an isothermal process, so the temperature will also vary. So there you have work done is equals to 1 upon gamma minus 1, and you have nr, and it's like T2 minus T1. Now this equation has been derived just by taking the ideal gas equation into consideration, right? So that's how this equation has been derived. So this is what you will get over here. Now if the process would have been irreversible, in like instead of reversible, it would have been irreversible. In that case, what would have been the work done? So if again in the vacuum, if you are trying to find out the work done in the vacuum, in that case the work done would have been 0. But in the ideal, like in not in the vacuum, right, when the gas is expanding adiabatically, in that case you will have work done, like work done. Okay, all right, so this is for vacuum, and this equation which I'm telling is the equation apart from vacuum, when you are not like when you are not going into the, like apart from the vacuum, like in the when you have some external pressure, that's what it means. So work done will be equal to NCVP external by P, and you have T2 minus T1. Okay, where P external is the external pressure which has been applied, P is the pressure of the gas. So that is the equation for the work done. Okay, because you will be having pressure being applied by the gas, right? That's why it is expanding. Although, yeah, there will be some pressure of the gas, there will be some external pressure. So external pressure is taken as P external, pressure of the gas is taken as P. T2 minus T1 is the temperatures at which you are doing that, and CV is your molar heat capacity at constant volume. N is the number of moles. All right, so we have discussed about work done in different processes and the equations related to them. Now let's talk about the starting of your thermodynamics, that is zeroth law of thermodynamics. What it says, let's say if A is some like process which is in equilibrium with B, all right, and this B is in equilibrium with C. So if it is so, in that case, it is necessary that your A and C will also be in equilibrium with each other. So that's what your zeroth law of your thermodynamics tells you. All right, so this is about the zeroth law. That's it. There is not much about it. Okay, that's just the equation, just the way how it works. Now, while going through all these topics, I just missed out a state function, so I just thought to include this in at the end. So, state function is very important property when you talk about a particular thermodynamic state. So function, you all know, function means something which depends upon the other factor. When the other factors changes, it also changes, right? So function is what, let's say if I talk about fx is equals to 2x square plus 3x plus c, or anything, right? Let's say it's 6. So what does this mean? This is function of x. That means it depends upon x. If you change the values of x, you'll be getting different values of the function itself. So state function, so function basically is that thing, right? So there can be different values which could have been changed, like the temperature, pressure. So in the thermodynamics, we'll deal with these as the variable. So here the variable is x, whereas when we talk about thermodynamics, their variable will be temperature or pressure or volume. So when you change the values of temperature, pressure, or volume, the function or some other values, if they depend upon them, they are called as functions of that. So your state function is a thermodynamic quantity basically, which depends upon the initial and the final values of the variables. That's it. It does not depends upon which path you have followed in order to go to that particular place. For example, let's say we have some different value of pressure and volume over here, and we have a particle at some state A, let's say, and we have to go to some state B, let's say, right? So you can go up from A to B through this particular path. You can either go from A to B through this particular path, and you can also go from A to B through this particular path. So these are my three different paths. This is, let's say, path small a, this is path small b, and this is path small c. So those like thermodynamic quantities whose value does not changes or does not depends upon which path you have followed to reach from a to b, either you are following path a, path b, or path c, that does not depends upon that. It just depends upon the states or where that particular particle is. So these kind of functions or these kind of thermodynamic variables, thermodynamic functions, they are actually called as the state functions. Okay, it looks little complicated in understanding, right? But it's pretty simple. See what it is. If you have certain particle, let's say you have a glass of water. Okay, let's say you have a glass of water with you. So in that glass of water, you can measure the mass, you can measure the temperature, right? So these are the like things which you can measure and which can act as a variable. Now if you want to calculate the enthalpy of the enthalpy of the water in the glass, so that you cannot do. Okay, that you cannot do, because that enthalpy is the state function. That depends upon the state of the water inside the glass right now. So how you will do that? So the easiest way is to just to like heat this glass up to a different temperature. Let's say right now it is at temperature T1. Heat it up to a different temperature T2. Now the difference between these two temperatures T1 and T2, that's where you are going to that's how you can calculate your enthalpy of the glass of water by this equation, that is delta H is equals to Cp dt, where dt is the change in the temperature, Cp is the uh, heat capacity of the water inside the glass, right? So by knowing the by knowing the two different temperature values, you can calculate the enthalpy of the glass. Now it does not depends, it does not matter that from T1 to T2 how you went. Either let's say if T1 is, let's say T1 was let's say 600 degrees Celsius and T2 was, let's say 200 degrees Celsius. So from 600 to 200, how you went, it does not depends, like delta H value does not depends upon that. It might happen that from 600 degrees Celsius you first cooled it up to let's say 400 degrees Celsius, then from 400 degrees Celsius you again cooled it up to 200 degrees Celsius. So if you have done so, so in that case from here to here, let's say you have calculated H1, delta H1 by the same formula, putting the different value of temperature like T1 as 600 and T2 as 400. Again from here to here, let's say you have calculated again by putting the values at delta H2. So your delta H, okay, delta H from here to here can be calculated as sum of delta H1. So delta H can be equal to delta H1 plus delta H2. So the value of delta H does not depends whether you are going through like by a different path or you are going directly from the initial to the final value. All right, so these are called as state functions. State functions is very simple. It's just the thermodynamic variable which defines the state of the system. Okay, so these like these functions are given very much priority in your thermodynamics, and that's why they are always written in a capital letters. Okay, so wherever you will find state functions, they are written in capital letters. Let me write down some of them. So you have enthalpy. Okay, just now I show you. So capital H, then your entropy given by capital S, then your internal energy. Okay, internal energy that is given by capital U. Then you have free energy, Gibbs free energy. Okay, Gibbs free energy. So that is given by delta G. Oh, sorry, that is given by capital G. Then you have Helmholtz free energy, right? Uh, Helmholtz free energy. So that is given by A, right? So all these like all these are example of your state function. Even your volume is an example of state function which is written as capital V. All right, so whereas some of the functions which are not state functions are like your work done is not a state function, so it's not a state function. Heat given to the system is not a state function. That's why that is written in small letters, small q, small w, like that. Okay, so in this video, I have tried to cover all the basics part, apart from like first law of thermodynamics. So up till that, I have covered all the things. Now let's take some questions which have been asked from this much part only in your CSIR-NET. Okay, so I'll be taking those questions and I'll try to explain you that how you can solve them. In the next video onwards, I'll be explaining from your first law of thermodynamics. All right. All right, so we'll be taking these three questions which have been asked in previous years of your CSIR-NET and GATE exam. The first one over here, which you can see, was asked in your GATE 2010 exam basically. And it says among W, that is work, Q, that is heat, U, that is internal energy, and S, that is entropy, which are path function and which are state functions, right? So just now I told you that the state functions are generally represented in capital letters, and I told you that what are the sum of your state functions, right? So state function I have given you as internal energy, I have given you as entropy. I have not given you work done. Work done was not a state function, it was a path function. Similarly, the heat given to the system was also a path function. So option D will be the correct answer for this. That is, that says that W and Q are the path function, but U and S are the state functions, right? All right. Now the next question, it says which of the following is not exact differential? Okay, now this is also a property of a state function basically, that a state function is an exact differential. Okay, state functions, I'll just write down state function are exact differentials. Exact differential. What does that mean, exact differential? It means that if let's say z is a state function of some variable x and y, so basically you can write down this dz or dz as dz by dx into dx at constant y, and plus it should be del. Okay, so del z by del x. Similarly, del z by del y at constant x and dy. Okay, so you can write it like this. So these are called exact differentials. So a state function is an exact differential. It says that which of the following is not exact differential. That means you have to find out that which of these is not exact. Sorry, it's not a state function. So easily you can tell, right, that your heat absorbed by the system is not a exact. Sorry, it's not a state function, so it will not be an exact differential. Now, this question was asked for 2 marks in your CSIR June 2017 exam. It says that the correct statement for any cyclic thermodynamic process is. So, for any cyclic thermodynamic process, this is also a property of your state function, and the property says that if you are taking the surface integral over a closed path for any state function, okay, for any state function, that will be equal to 0. So for any state function, if you are taking integral over a closed path, that should be equal to 0. Now if you look upon this, so you have four different options where the only, like, this is not a state function, right? The first one is not a state function. Similarly, this work done is also not a state function. Here, volume into dq is not a state function, so again this is not a state function. The only one which is state function over here is u, that is internal energy. And and yeah, for internal energy, obviously if you take the integral over a closed path, it is going to be equal to 0. So your correct option will be option number 3. So just from the introduction part, you can see that there are question asked in the previous year's exam. That's why thermodynamics is very important from the basics itself, right? So this was the first video of this series. I'll be making the next video on the first law of thermodynamics very soon. So stay tuned for that. If you are not subscribed to the channel, do subscribe the channel. If you like this video, give it a like. If you want to ask anything, you can ask that in the comment section below. And that's all from my side for this particular video. Thank you so much for watching, guys, and have a great day.